Alright, so this could be our next notes in algebra. This is going to be chapter 6, lesson 1. And before this we were looking at inequalities, and we've looked at linear equations and so on. And now we're going to be looking at something a little bit of a different idea. You can kind of see this word here, systems of equations. Well, we're going to be kind of looking at what that all means and things we can do with it, like substitution and addition and subtraction. And that's going to kind of be our next 2, 3, 4 lessons. And this can be a little bit more difficult. I'm going to give you some vocabulary here to start off with. Make sure you add this to your notebook. Make sure you ask questions in class. When we go over, just a quick review of this and we go over problems, make sure that you're asking questions. Okay, so first word we see here that's pretty important is systems of equations. So, and this, all a system of equations is, it's a group of equations with the same set of unknowns. Okay, so we might have like y equals 3x plus 2 and y equals negative x minus 17. And that we put them together, we'd make them a system of equations, and we'd see how many answers for each of them are the same. Okay? And you solve these system of equations by finding the values that will satisfy both of the equations. Sometimes it's just two equations, and that's really what we're going to be looking at. Just keep that in mind. So there's also some vocabulary to keep in mind with systems of equations, and one of them is something called consistent. So if you have a system of equations and they have one intercept, we call that consistent, where it has just one solution. And if we were to graph them, it would kind of look like this right here, this top one. Okay, that's a consistent, and it's also independent in that it only has one answer. So you'd see these two different graphs, they're going different directions, and they have one point where they meet. That's called consistent, and they call it independent when they only have one answer. Okay? And then, like you see here, I'm seeing on my notes, so only one solution, we call that independent. When the solutions are infinite, we call that dependent. And if we looked at a graph of that, it's this bottom one here, we only see one graph, right? That's because they're overlapping, and then they just all have a, just an infinite number of answers, and they're the same answer. Okay, so that's what that's going to look like. All right. And if the system of equation has no solution, we call that inconsistent, and then the graph for that would be parallel and would look something like that. So we'd have two lines, two linear equations, we'd graph them, and we see they never cross, they're parallel. Okay, so that's kind of some of the terminology we're going to use. Let me pause this, I'll go to the next page. So what I'm going to show you here next is, well, how do you apply this? How do you graph these and then see what the solution for that system is? Okay, so here we have two linear equations, y equals negative 3x plus 10 and y equals x minus 2. And what we're going to do is we're going to take a piece of graph paper and we're going to graph this. And let me get the piece of graph paper out. I'm going to pause this here. I'm going to get the graph paper ready to graph, and then we'll go over, or I'll go over with you how to solve these problems. Okay, so I got this piece of graph paper ready, and what we're going to do is we're going to take each one of these and we're going to use these. They're in slope-intercept form, and because we can see the slope right here, negative 3 for this one, and this is 1, and we can see the y-intercepts, 10 and negative 2, and these will be easy to graph. We're going to do that really quick and then see where they end up. So let me show you. So this one right here, the y-intercept is 10, and that means 0, 10. So if we look at this graph right here, these are each 2, so 2, 4, 6, 8, 10. That's our 0, 10 right there. That's one of our points. And then we know it's a negative slope, so the line is going to be going down, down 3, and over 1. So we're going to go 2, 3, over 1. It's going to be right there. Then we're going to take a piece of, or a ruler, not a piece of anything, we're going to take a ruler, and we're going to graph it. Right there. Okay, pretty close. And then we then want to do y equals x minus 2. So then we got minus 2. So we're going to go down there and show it to you. There's negative 2. And then we know the slope of that one is up 1 and over 1. So I'm going to do a little bit more on this one. So up 1 over 1, up 1 over 1. So it's going to be right about there. And then I'm just going to graph this one. Okay. And we got a point right here that crosses. Okay. So this, we could even write them. Y equals x minus 2. And this is going to be y equals negative 3x plus 10. So that's our two graphs. That's kind of where we start. And we see we have a consistent independent. It looks like we have one place they cross. And we kind of see it looks like a 1, maybe a 1, 2, 3, or a 4. And we could see what the answer is just by plugging in to the equations and see what we come up with. Okay, so let me pause here and I'm going to get some of that prepped. Okay, so again, we're kind of looking at this and we're saying the y is 1. So the point where they cross is 1 for y, and then we're going to say it's pretty close to 3. We're going to guess that that's what it is. And then we're going to take that answer and we're going to plug it into the equations and see if we plug that in for x, that's what we get for y. So let's do that. So we have here y equals negative 3 times 3 minus 2. Okay. And, oh, I'm sorry, not minus 2, plus 10, right? And so we get y equals negative 3 times 3 plus 10. So we get negative 9 plus 10, and that gives us y equals 1. And that's kind of what we have, right? So if we plug in 3 for x, we get 1 for y. Works for that one. Let's check the other one then. Y equals x minus 2. And that's going to be y equals 3 minus 2, and then y equals 1. Same answer. So then we know the solution for this is 3, 1. The point where those equations intersect is the point 3, 1. And that's kind of how you use them. You draw the linear equations out, and you can graph them on a coordinate plane and see where they cross, and then see if that point works for the intersect. So another thing we can also do with this is we can turn these things from words into equations, and then we can solve them. Okay? And this is from page 341 in your book. And the problem says the number of girls participating in high school soccer and track and field has increased steadily over the past few years. It says use the table to predict the year of participation will be the same for each sport. So here's the table. You can look on your book as well. I kind of abbreviated a little bit, but it fits what it says in the book. So we got soccer. We got in 2007 we had 345 students. In 2012 we had 371 students. And that kind of gives you the slope, right? The change. And then track and field 458, and then in 2012 467. And then we can graph that, or we can figure out that change over the years, and that'll give us a slope. Okay? So let's see how we can use that to turn it into an equation. Okay, so first thing we want to do in that equation is we want to find the rate. So here we have 371 minus 345, and then we divide that by change in years. That's 5. It's going to be 5 for both. Okay, this one is pretty easy. Okay, so yeah, it should be an increase. It should be the other way here. So let's rewrite this. 458 minus 467. Looks like that's 9 over 5. Okay, for that slope. That's going to be our m in the equation. And then this one, 371 minus 345. I don't have my calculator. I'm just going to do it really quick. 26. So 26 over 5 is going to be that one. So an increase in 26 in 5 years. So that's kind of our m there. And there's not much to do with them. That would then be our slope. And then what we're going to do is we're going to say y is equal to the number participating, and x is going to be the number of years after 2012. Okay, so we're going to kind of plug it into this kind of equation, y equals mx plus b. And let me write that down, and then I'm going to pause this video and I'll get back to you once I have it written down. So I got these written out. So we're using y equals mx plus b. B is your y-intercept. For our y-intercept, we're going to use the starting point for each sport. So this one is soccer. We end up with 371 here, okay? And then this one is going to be track and field. We end up with 467 there, and yeah. So I think I actually did have this one right. I don't know why I was thinking I didn't, because you do minus the smaller from the larger. Okay. So and also you'll notice that I had these fractions up for 26 over 5, 9 over 5, and what I did was I reduced them into decimals. That's just going to work better for this graph. Okay. And then so then I have for soccer y equals 5.2x plus 371. That's our y-intercept. And then y equals 1.8x plus 467. This is going to be our increase. And you can see soccer is increasing much higher rate, twice as fast. So eventually it should catch up to track and field. And again, we're just trying to figure out if these two sports continue to increase, when will they have the same number of participant girls? So our next step is to graph it. So let me pause it and I'll get everything ready. So this is the graph I set up. The ranges for y and x, and then I'm just going to take those two equations. Let me grab them here. So I have y equals 5.2x plus 371, okay, and I'm just going to plug in a few numbers here just to see what'll work. And I'm going to go with 5 years, and this is going to be years after, so let me actually put that in, years after. And this is going to be number of students, right there. So we know that these start, each one starts 371, so this is like somewhere around here, right? And the other one starts at 470 or so, probably somewhere around there. Okay, and they're going to keep going up. We're going to plug in for each one 10. We'll just go from maybe 15. So let's plug in the number 15 for both of these equations and see what that gives us for the next point. So if we could do the math, we would then do y equals 5.2 times 15 plus 371. So we're going to get, if we do the math, 5.2 times 15 plus 371. It's going to give us 449 for that one. So it looks like 15. There's our 449. Right about there. Do the other one now. Y equals 1.8 times 15 plus 467. Do the math. $27 plus 467 gives us 494. It's almost 500. So somewhere about, probably about there. Okay. So then if we just kind of made a line here, let's do that. We do that, give me a second here. We see this point somewhere around there. And it's about 30 years or so. It's pretty close to that. Okay, so we might want to plug in and see if that works. Now these are a little bit more sloppier. We might not have exactly the right answer, but we might see if we can get that answer, if they're close. And then y, 5.2, let's go 30 plus 371. If we do that, 5.2 times 30, 156 plus 371, we get about 527. Okay, for that one after 30 years. And let's do the other one, y, 1.8, that up, times 30 plus 467, 1.8 times 30 plus 467, 521. Well, this one's a little bit over, and they might have crossed already, so this one's above that one, right, this 5.2, and it started below. This one actually started below. Now it has more students than track and field. So we would guess it's probably a little bit less than that. Let's just say 28 instead of 30. So y equals 5.2 times 28 plus 371. It's kind of how you have to do these. They're not perfect problems, but you can get a good guess at it. Plus 371. About 516.6. Might have to round that up. 517. A little bit less. Let's see what y gives us. Or 1.8 for track and field. So 1.8 times 28 plus 467. Let's see what that gives us. 1.8 times 28 plus 467. 517. Okay, 0.4, we'd call that 517. So somewhere a little less than 28. We could figure out exactly where that is if we just kept messing around a little bit, like 28.2. But you can see how it works. So we could say about 28 years in, and we could kind of see that from the graph again. About 30 years. And you know, you always want to be careful. Maybe I went a little bit high here. Maybe this one went a little low, and that could mess it up. So the more precise you are with the graph, and this one actually suggested about 29. So yeah, just be careful when you do these. That's how you kind of use systems of equations in word problems. Okay, so that's your notes. I gave you a little bit more this time because of the length of solving that problem. Hopefully that wasn't too difficult for you. A little bit longer, usually like 12-13 minutes. This one's a little extra, but I gave you a good example there in that problem. Make sure you add this to your notebook. Let me know if you have any questions in class. Maybe even look over the chapter in the book as well. And see you in class.